So my name is veera swamy, senior lecturer in electrical electron engineering, Government Polytechnic, Nirmal. I am teaching 5th semester subject AC motors, subject code 18E502C. Main topic: 3-phase induction motor, and subtopic: speed control of 3-phase induction motor. So before going to speed control, I will give a small introduction about 3-phase induction motor. 3-phase induction motor consists of two main parts: stator and rotor. Stator and rotor. In the stator inner periphery, we will place 3-phase winding. 3-phase winding. Generally, it is strong delta connected, and 3-phase windings are 120 degrees spatially separated, and when a 3-phase supply is given, a magnetic flux is developed. The magnetic flux currents also separated by 120 degrees with respect to time. And again, rotor. Rotors are two types. One is squirrel cage, another one is slip ring. You may get one doubt: what is the necessity of this introduction, that is stator and rotor? If you know the two main parts, from that side only we will control the speed, right? So next, rotors. Rotors are two types: squirrel cage and slip ring rotor. The main difference between salient and non-salient slip ring and squirrel cage is in squirrel cage, copper bars or iron bars are placed in a slots of the rotor and are short circuited at end rings by end ring rings. Therefore, the resistance is fixed in case of squirrel cage rotor. But in case of a rotor, in its outer periphery, in the slot, we will place a copper winding. We'll place a copper winding and 3-phase winding. 3-phase winding is connected to 3 slip rings. Right? Through that slip rings, we can add extra resistance to rotor circuit, right? That means resistance can be changed by using in a slip ring rotor, right? These are the two main parts of 3-phase induction motor, right? A 3-phase induction motor is a practically a constant speed motor, practically a constant speed motor, right? More or less like a DC shunt motor, more or like a DC shunt motor. The speed variation of DC shunt motor is possible within the wide range with good efficiency merely by manipulating a simple field rheostat. The same is not possible with induction motor. The same is not possible with the induction motor. In case of induction motors, the speed variation is accompanied by a corresponding loss of efficiency, right? By reducing the efficiency, by controlling the speed, efficiency is reduced. That is why it is much easier to build a good variable speed DC shunt motor than a variable speed induction motor. Right? So induction motor is a practically constant speed motor. That means for the entire loading range, the change in speed of the motor is quite small. Quite small. But the speed of a DC shunt motor can be varied very easily with good efficiency. But in case of induction motor, speed reduction is accompanied by corresponding loss of efficiency and poor power factor. One more important thing is another factor, that is a poor power factor. Poor power factor. An induction motor are widely being used. Their speed control may be required in many applications, and different speed control methods of induction motors depends upon the two types and two sides. We can control the speed on two sides, that is stator side, another one is a rotor side. Stator side and rotor side. Speed control of three-phase induction motor can be done from stator side, and then one is a rotor side. I'm already discussed different parts of three-phase induction motor, that is main parts are stator and rotor, right? From the stator side we can control the speed by using stator side parameters. From rotor side also we can change the speed control. In the stator side, by changing the supply voltage, we can change the speed of induction motor. Second one is by changing the supply frequency. We can change the speed of induction motor, right? And third one is by changing the number of stator poles. Right? These only by these three parameters, by using the three parameters, we can change the speed. On the stator side, we are giving only voltage, right? That's why by changing the voltage, we can change the speed of the induction motor. After giving the voltage, what happens? A magnetic field will be developed. And EMF is induced in the rotor circuit, right? So by changing the supply frequency, so the induced EMF, the rotor also changes, right? So by changing the supply frequency, we are applying a three-phase supply. It is a 50 Hz frequency, three-phase supply of 50 Hz frequency. Suppose if we change the frequency on stator side, then we can change the speed of induction motor. And third one is by changing the number of stator poles. We change the number of stator poles, right? Here stator poles, on stator side we have stator poles, right? Stator poles is given by, suppose speed n is equal 120 f by p, speed ns is equal 120 f by p. The speed is varies, 120 is a constant one, f is a frequency, and p is number. By changing the frequency and number of poles, we can change speed. Similarly, by changing the supply voltage, right? So we have three types of methods, three methods on stator side, three methods on stator side. And next, rotor side. And rotor side, again, one is a squirrel cage, another one is a slip ring, right? So it is possible only in case of slip ring induction motor, only in case of slip ring induction motor. By rotor rheostat control method, by connecting a rheostat in the circuit to the slip rings, we can change the speed. By injecting the EMF in the rotor circuit, again through the slip rings, right? So these two methods are applicable only for slip ring induction motor. And third one is by cascading connection. By cascading of two induction motors, so we can get two different speeds. We can get two different speeds, right? So these three methods are so why it is called a how we will get a speed control by using a cascade connection means simply two motors are connected mechanically and output of the rotor output, slip ring motor output is connected to the input of the another motor. So it is again rotor side. So output of the rotor is connected to the input of the another rotor and they are mechanically coupled. So that's why this is also comes under stator side. So rotor side, right? There are three types of speed controls in stator side and three types of speed controls on rotor side. On rotor side, right? So on stator side, first one is by changing the supply voltage, another one is by changing the supply frequency, and third one is by changing the number of stator poles, Next, by rotor side, by rotor rheostat control method, by changing the EMF injected in the rotor circuit, and another one is by cascading the connection of two induction motors, right? So this, by using these six methods, we can change the speed of the three-phase induction motor, right? So but that variation is very simple, very little bit variation occurs, a small variation in the speed is obtained. Not like a DC shunt motor. In a DC shunt motor, so we can get more speed variations when compared to the three-phase induction motor. Why I am comparing the DC shunt motor with three-phase induction motor means both are constant speed motors. Three-phase induction motor is a constant speed motor and a DC shunt motor also a constant speed motor, right? That's why I am comparing the two motors, right? We can get variety of speed controls in a DC shunt motor without losing efficiency. But in case of a three-phase induction motor, by losing some efficiency, so we can obtain a small variation in the speed, and again some poor power factor, right? So induction motors is practically a constant speed motor. That means for the entire loading range, change in speed of the motor is a quite small, and speed of a DC shunt motor can be varied very easily with good efficiency. But in case of induction motors, speed reduction is accompanied by corresponding loss of efficiency and power factor. As induction motors are widely being used, their speed control may be required in many applications. So there are different speed control methods are there. One is the stator side, another one is a rotor side. stator side by changing the supply voltage and by changing the frequency and by changing the number of poles, and rotor side by connecting a rheostat in the slip rings in the rotor circuit by injecting the EMF in the rotor circuit. And third one is by cascading of two motors. One is a slip ring motor and another one is a squirrel cage motor, right? The other one is a squirrel cage motor. So we can get the speed control to variable speeds by cascade connection. Very important method, right? So today we will discuss the first three types, that is cascade connection, on stator side, that is by changing the supply voltage and by changing the supply frequency and by changing the number of stator poles. Let us consider first one, that is by changing the apply voltage. By changing the apply voltage, we can change the speed of three-phase induction motor. So let us consider from the torque equation of induction motor. Torque equation is given by K1 into S into E2 square into R2 by square root of R2 square plus SX2 whole square, that is equal to, where K1 is 3 by 2 pi ns into S into E2 square into R2 by square root of R2 square plus SX2 whole square, right? So from the torque equation of induction motor, here the rotor resistance R2 is a constant one, and if slip is S is small, then S into x2 whole square, S into n under running condition, Sx2 whole square is also so small, so it can be neglected. Therefore, torque is proportional to S into E2. So where E2 is the rotor induced EMF and U2 is proportional to V. Thus, torque is directly proportional to S into V2. That is, torque is proportional to finally S into V2, which means if supply voltage is decreased, then what happens? The developed torque also decreases. Hence, for providing the same load torque, the slip increases with decrease in voltage, right? Here the torque is equal to some constant into S into V2, right? A torque is proportional to S into V2. If torque decreases when voltage V2 decreases, right, or some load on the induction motor is increased, if the supply voltage is decreased, then the developed torque also decreases. But it is already on some load. To provide that load, torque must increase. Hence, for providing the same load torque, the slip increases with decrease in voltage. So consequently, speed decreases. When slip increases, so slip and speed are inversely proportional. N is equal to 120 F by P. 120 into F by P, right? Where S and slip. Suppose when rotor rotates with synchronous speed. What happens? Synchronous speed, right? Slip is equal to 0. Then slip is equal to 0, right? Suppose when slip at starting, what happens? NR is equal to 0, slip is equal to 1. Right? That means when NR is equal to 0, S is equal to 1. When rotor speed is increasing, what happens? When rotor speed increasing, slip decreases. So here, for getting a load torque, the slip increases. When slip increases, automatically speed decreases. They're inversely proportional. So why? Because when NR is equal to 0, S is equal to 1. When NR is equal to NS at higher speed, it is equal to synchronous speed. S is equal to 0. S is equal to 0. They are inversely. If it is high, it is 0. If it is 0, it is high. Right? They are inversely proportional. This means the easiest and cheapest still rarely used because large change in supply voltage is required for relatively small change in speed. So one is it is cheapest. First advantage is very cheapest. The most disadvantage is by changing the large supply voltage will result in a small change in speed, right? Relatively small change in speed. A large voltage supply voltage will result in a large change in supply flux density. Hence, this will disturb the magnetic condition of the rotor, right? So that's why we cannot change the supply voltage very large. Why? Because it affects the magnetic conditions of the rotor. Magnetic conditions of the rotor, right? So in this way we can change the speed of a three-phase induction motor, right? So very simple, you have to observe that torque equation, right? So if you understand the torque and torque proportionality, then we can easily understand the speed control, right? So here observe the torque equation. From the torque equation of induction motor, rotor resistance R2 is a constant, and if slip S is a small, then Sx2 whole square is so small, and then it can be neglected. So therefore, and R to R to cancel out, then torque is proportional to S into E2 square, where E2 is a rotor induced EMF and ut is proportional to v. So thus torque is equal to S into V square. Torque is proportional to S V square of the voltage, right? So very important relation, torque is equal to S into V2 square, square of the voltage, which means if the supply voltage is decreased, the developed torque decreases. Hence, by providing the same load, torque, the slip increases with decrease in torque, with decrease in voltage, and consequently the speed decreases. Torque speed and slips are inversely proportional. When voltage decreases, torque decreases. When torque decreases, slip increases. When slip increases, speed decreases. But this method is easiest and cheapest, and still they are rarely used. Cheapest and easiest, but rarely used. Why it is rarely used? This method is easiest and cheapest but still rarely used because large change in supply voltage is required for relatively small change in speed. So large change in supply voltage will result in a large change in flux density. Hence, this will disturb the magnetic condition of the rotor. This will change the magnetic condition of the rotor. So that's why. So it is rarely used. If large change in voltage occurs, so it will affect the magnetic condition, right? So that's why. So this method is rarely used. Then we will use. Then we'll go for number of change in the supply frequency. A constant and second one is on stator side by changing the supply frequency. The synchronous speed of rotating magnetic field of induction motor is given by synchronous speed of induction motor, where F is equal to frequency of supply voltage, P is the number of poles, and synchronous speed is equal, Ns is equal to 120 into F by P. 120 into F by P, right? So that means Ns is equal to 120 F by P. F is directly proportional to speed, and the synchronous speed changes with change in supply frequency. Actual speed of an induction motor is given by n is equal to ns into 1 minus s. N is equal to n into n means here nr, rotor speed is equal to ns is equal to 1 minus s. However, this method is not widely used. It may be used where the induction motor is supplied by dedicated generator so that the frequency can be easily varied by changing the speed of the prime mover. And also at lower frequency the motor current may become too high, the motor current become too high due to the decreased reactance. So, and if the frequency is increased beyond the rated value, the maximum torque developed falls while the speed rises, right? So we know that synchronous speed is given by 120 into f by p, where nr is equal to 1 minus s into ns, that is equal to 1 minus s into 120 f by p, 120 f by p, right? By gradually changing the supply frequency n, supply frequency of ns, and hence the motor speed can be increased by decreasing the frequency. By changing the frequency, and speed can be increased or decreased smoothly. So provisions for supply of variation frequency can be made by consumer by having separate arrangement such as solid state equipment or rotatory converter. Solid state equipments are rotatory converter. So this method so far had limited applications because of cost involved in arranging a variable frequency power supply. With the recent developments in semiconductor devices, frequency control method of speed variation of induction motor is becoming popular, right? The simply by changing the supply frequency, right? Speed is directly changes, right? Rotor speed is equal to ns is equal to 1 minus s. When ns changes, automatically n changes. N is equal to ns into 1 minus s, right? Where ns is equal to 120 into f by p. When f increases, when frequency increases, synchronous speed increases. When synchronous speed increases, and rotor speed also increases, that is n is equal to ns is equal to 1 minus s, right? So so simply by changing the supply frequency, we can change the speed of three-phase induction motor, right? But once again, however, this method is not widely used. It may be used where the induction motor is supplied by a dedicated generator. So that the frequency can be easily varied by changing the speed of prime mover, right? By changing the speed of prime mover, so the induction motor is connected to generator. By changing the speed of the prime mover, automatically supply frequency also generated, directly connected. Suppose the supply frequency, this induction motor is directly connected to generator, the dedicated generator is connected. In that case only we can achieve this type of speed control, right? And also at lower frequency, suppose this frequency increases, speed increases, but at lower frequency what happens, the motor current may become too high, due to decreased reactance, right? When frequency is equal to 50 hertz and frequency increases, in the reactance increase. When frequency decreases, reactance xl is equal to 2 pi fl, reactance is equal to 2 pi fl. When frequency decreases, reactance decreases. When reactance decreases, current increases. Okay, due to decreased reactance, current increases. At lower frequency, the motor current may become too high due to decreased reactance, and if the frequency is increased beyond the rated value, right? And if the frequency is increased beyond the rated value, and maximum torque developed falls while the speed rises, torque decreases and speed rises, right? This is only when dedicated generator is connected to the induction motor. Suppose when it is not connected to the generator, then a separate arrangement is required. Separate arrangement is required to control to apply the variable frequency, right? So generally we are using semiconductor devices, right? uh, Variable frequency power supply. We have to supply variable frequency all frequency. With the recent developments in semiconductor, frequency control method or speed variation of induction motor is becoming very popular. Very popular. A fundamental black diagrams. I will show the fundamental black diagram of speed control of variation of induction motor by using thyristors. By using thyristor, right? So I will show this. And converter, a three-phase supply. So by connecting a dedicated generator, simply by changing the prime mover of the generator, automatically frequency changes. Suppose it is connected to only three-phase supply, we have to use separate arrangement. Observe the black diagram. A three-phase supply input and a converter, phase control circuit, and a converter converts AC voltage into DC voltage, and the DC voltage passes and again given to an inverter, right? And again a part of the DC voltage is given to voltage to frequency converter. It convert voltage to frequency converter, right? Next, by using that, by the output of the voltage to frequency converter is connected to inverter firing circuit diagram. The inverter firing circuit diagram will fires the inverter. Then we get output is a three-phase variable voltage frequency output. Right? A three-phase supply at the input is first converted into collected controlled DC. Then DC is applied to the inverter circuit, whose frequency is controlled by pulses from voltage to frequency converter ratio, voltage to frequency converter unit. A large smooth reactor L is connected to the circuit to filter the controlled DC. Right? So this is also known as voltage V by F control method. So in this method, right, so only by changing the frequency, also we can change speed, right? Here by changing the speed, so by changing the frequency, speed changes. But in this case, suppose if it is dedicated generator is connected to three-phase generator. Suppose when it is not dedicated generator, suppose if a three-phase supply is given, so how to change the frequency of three-phase induction motor, right? There is one method is simply by connecting a thyristor circuit or semiconducting device in between supply and do the road motor. In between supply and motor, you have to connect a circuitry, right? So it was shown in the block diagram, right? Simply the convert a three-phase supply into three-phase variable frequency supply, three-phase variable voltage frequency output, right? So first converting AC voltage into DC voltage, and a controlled DC voltage again given to an inverter, and the inverter, by changing the firing circuit, we can change the output voltage and frequency. Right? So this is about speed control by only by changing the frequency. And next, by using this circuitry, so another important method, it is also comes under frequency, but this method is known as V by F control method. This again we have one more control, that is V by F control method. A constant V by F control of induction motor. Constant V by F control method. A voltage separately by changing the voltage. A large change in voltage, where a small change in the speed will occur. The first method. The second method, by changing the frequency, by simply converting by simply connecting a dedicated generator to three-phase induction motor, we can change the frequency. By changing the prime mover speed, frequency changes. Or by using a thyristor circuit, so it will convert an AC voltage into a single three-phase supply is converted into DC supply, and DC supply is again converted into inverter, can be given to inverter, and inverter output may be a controlled voltage and frequency. We can control voltage and frequency by using this circuitry, right? So we can control voltage and frequency. So that we will discuss. Third one, that is a constant V by F control of induction motor. This is the most popular method for controlling the speed of an induction motor. As the above method, that is simply frequency is reduced, keeping the rated supply voltage, the air gap flux will tend to saturate, right? There is a one drawback in only by changing the frequency. By only changing the frequency, what happens? Keeping the rated supply voltage, the air gap flux will tend to saturate. Right? So this will causes the excessive stator current and distortion of the stator flux wave. Right? Excessive stator current and distortion of the stator flux wave. So therefore, the stator voltage should also be reduced in proportional to the frequency, so as to maintain the air gap flux constant. Clear? Very simple thing. This is the most popular method for controlling the speed of induction motor. It's a very, very popular method. Generally, in all industries, they are using this type of control method. Very easiest method, right? Suppose if you consider only previous method, only changing the frequency, what happens? If the supply frequency is reduced, keeping the rated voltage constant, the air gap flux will tend to saturate. Why? Because when frequency decreases, you know that induced EMF in the rotor circuit or induced EMF in the stator is given by 4.44 into 5 into F into N. 4.44 into 5 into F into N. Clear? Suppose voltage is constant, right? If you decrease the frequency, is equal 5F N. N or number of turns are constant. 4.44 is a constant, and frequency and magnetic flux. When frequency decreases, what happens? Again, we are maintaining a voltage constant. Frequency decreasing. To maintain a voltage constant, flux increases. Flux goes to saturation. Right? Flux increases. That is a major drawback. Is only by changing the frequency, what happens? The magnetic saturation occurs. The air gap flux will tend to saturate according to E is equal to 4.44 into 5 of N into 5 of into N. Suppose if you take E1 or E2, it is EMF into the stator or rotor, stator side or rotor side, right? So when flux increases, it's proportionally V must be decreased, right? So therefore the stator voltage should also be reduced in proportional to the frequency, so as to maintain the air gap flux, constant. So the magnitude of the stator flux is proportional to the ratio of the stator voltage and frequency, right? So we have to change voltage and frequency proportional. You have to maintain V by F ratio constant. The magnitude of the stator flux is proportional to the ratio of the stator voltage and frequency. Right? If V by F is a constant, automatically flux also remains constant. Hence, if the ratio of voltage to frequency is kept constant, then the flux remains constant. The flux remains constant. Also, by keeping V by F constant, the developed torque remains approximately constant. By keeping the V by F constant, the developed torque also remains approximately constant. This method gives higher runtime frequency. Higher runtime frequency. Therefore, majority of AC speed varies. Majority of AC speed drives employ employ a constant V by F method or variable voltage, variable frequency method for speed control. So along with the wide range of speed control, this method also offers soft start capability. Very simple thing is, so the drawback in the previous method, that is by changing only the frequency. One drawback is there, that is flux saturation. Air gap flux becomes saturated, right? Why it is saturation? Why it is saturating? You know that the induced EMF E or voltage is proportional to flux and frequency. When frequency decreases, voltage decreases. When frequency decreases, voltage decreases. When voltage decreases, voltage must maintain constant, so flux increases. When flux increases means it goes to saturation, right? So that's why always maintain V by F ratio constant. In frequency control method, we have to maintain V by F ratio constant. You have to change the frequency. We can increase or decrease the frequency. We can increase or decrease the frequency by using a converter-inverter method. Converter-inverters, we can increase and decrease the frequency. But at the same time, you have to maintain voltage constant. Suppose if you decrease the frequency, you have to again decrease the voltage V, thereby V by F is always constant. When V by F is always constant, then automatically right, torque remains constant, each and every, and air gap flux also remains a constant. So that's why in most of the devices, most of the speed control machinery, three-phase, we will use V by F control method. V by F control method. So very useful method. So summary, right? A three-phase induction motor is practically we know that three-phase in summary. So I will discuss few words about today class. That a three-phase induction motor is a constant speed motor, right? And speed control, we can control the speed of the motor by two ways, by stator side and rotor side. On stator side, we are applying a voltage V, three-phase voltage V. So by changing the voltage, we can get variable speed, and we are applying a frequency also. By changing the frequency also, we can change the speed of induction motor. And third one is by changing the number of poles. So by changing the number of poles means you have to design the three-phase induction in such a way that two different poles. Design the stator for two different poles, right? So two different speed. Then automatically, if you choose the one for two poles, the speed is different. For four poles, speed is different, right? On stator side, there are three methods: by changing the supply voltage, by changing the supply frequency, and third one is by changing the number of poles. Or in the supply frequency, in changing the supply frequency again. So one more important thing is not only change the frequency, you have to change the voltage also. That is the third method is V by F control method. Right? In all these methods, first one is by changing the supply voltage, right? By changing the supply voltage, what happens? So torque is proportional to S into V square. By changing the supply voltage, what happens? Torque decreases. When torque decreases, slip increases. When slip increases, speed decreases. By increasing the voltage, speed decreases. Right? But it is very a small variation of speed will occur due to a very large change in the supply voltage, right? And second method is a frequency control method. So by dedicated generator is connected to the supply to three-phase induction motor. By changing the prime mover speed, when speed can be changed. When speed increases, speed also increases. Speed of induction motor also increases. But there is one drawback in that. Suppose if the frequency decreases, what happens? Air gap flux changes. It goes to saturation. That's why we will go for V by F control method. V by F control method. In V by F control method, we will vary voltage and flux also. Voltage and flux. Voltage and flux. So when flux decreases, voltage must be decreased. So V by F ratio must be constant. V by F ratio must be constant. Right? Thank you very much. Have a nice day.